CHEM200. You just finished up an exam and now we're back in the routine of new lecture material. So I hope you had a break after the exam. There was no homework. Now homework is back up. So chapter 6, ready to go. Come see me during office hours if you want to talk about exam, quizzes, homework, lecture material, any of that, come see me. As usual, it's going to take about a week and a half to get the exams back. Quiz 4, not too far off, April 20th. Please note the withdrawal date has been moved to May 8th. So let me know if that's something you're considering. We can talk about that. We will talk about the class theme as we move in to this next section for exam 3. And please note, we're doing bonding still. Okay, you did Lewis bonding theory, Vesper theory, those theories you're very familiar with. You take a look here, and it's very likely this is new. Okay, so this is a new bonding theory in this part 1. Part 2 has a different bonding theory. That's what April 13th, April 15th are new bonding theories. So that's what we'll be focusing on. New information, some interesting chemistry as well. So before we get on the chemistry, this is actually the last installment of our theme, our Olympic themes. So a couple of things. We'll revisit these throughout the rest of the semester, but the last is all about recovery. Okay, so you took an exam. Things have obviously been a big adjustment for all of us. So really encourage you to think about listening to yourself, take breaks, take measures to speed recovery. I know for me it's hard to get back in the groove once I've taken a nice long break, but do what you need to do, take speed recovery, and then start back at it. So that's the plan for today, is starting back at it with chapter 6. So I want you to pay close attention to this first image. This is what we're going to come back to in a few things. This is liquid oxygen right here, and it's being poured through this magnet. You see this magnetic poles, and you can see that it's attracted to the poles of the magnet. Okay, so that should tell us right off that's liquid oxygen and it's magnetic. Okay, so we've already talked about magnetism, and we should take us to some definition of paramagnetic, diamagnetic. Okay, so diamagnetic, all the electrons are paired. Paramagnetic, it's unpaired. Well, what we've done in Lewis theory is showed that oxygen looks like this. Well, what we're seeing, physical measurements, is saying that liquid oxygen is magnetic. If all the electrons are paired like this, it would not be magnetic. So you can see bonding theories have limitations. Specifically, the Lewis bonding theory has limitations. That's why we're spending our time on these new theories. So the first idea is thinking about what forms bonds. Okay, so if we're interacting two hydrogen atoms, you can imagine if the hydrogens are very, very far apart, there's not much attraction. And then you can imagine if they're very close together, the black dots represent the nucleus. So those are the protons. If those are protons next to protons, those want to repel. So that's not very stable. So there's some in-between state, this balance of attraction, less repulsion, and that's this minimum here. And that's the bond length between how we normally draw a diatomic hydrogen. So what we're looking at is s orbitals and the way they overlap. So this theory takes us back to orbitals. Okay, so we need to think quite a bit about what does an s orbital look like, what does a p orbital look like, and now we're going to overlap those orbitals to form bonds. So this is called the valence bond theory, and our valence electrons are in orbitals that we've already seen, atomic orbitals. So that's s, p, D, and I know we kind of left off of these D and F, so we're like, they're crazy looking, they're, don't worry too much about them. But definitely know what the shapes are of an S and P. And then we're going to talk about hybrid orbitals as well. This is a combination of atomic orbitals. We'll see that. So here's the definition of a bond. Valence bond theory. A bond is the overlap of two half-filled orbitals. So if we have, like we did with the hydrogen, s orbitals, and they overlap, the electrons spin pair. You see my electron up, electron down, and that's a bond. And then you can determine the shape of the molecule determined by the shape of the overlapping orbitals. Well, good news, these shapes are the same shapes that you've already seen before. So there's not going to be memorizing new shapes in this, but it's all based on the orbitals. So that's what we'll see here. So let's do a couple of examples. First example is H2S. So you can take a look. This takes us back to orbital diagrams. Hydrogen, one valence electron each for both of those. Sulfur, you can see the electrons in the s orbital, the electrons in the p orbital, and then you can see we've got some places that are open for bonding. Okay, if we have a half-filled orbital that overlaps, that's the bonding. So you can see the arrows connecting these. This is filled, so it's not going to bond. And if you take a look, we've got p orbitals around this s. So we've got the py, px, pz, but those are the p orbitals. One is fully filled, and then two of them are half filled. So the hydrogens come in, and these p orbitals on the xyz axis, you can see, are 90 degrees apart. Okay, so that tells us H2S, according to this theory, has bond angles of 90 degrees. Well, let's go back to our Lewis theory for a minute. Lewis theory shows us this is H2S as well. Shows us there are two electrons, and we would say, well, that's a tetrahedral electron geometry. There's two lone pairs, so that would be less than 109.5. That's as good as we could get with Lewis and Vesper. And this says it's 90. Well, that's a little bit far apart. True value, the bond angle is 92 degrees. So this, you can see the validity of this model. This showing us the atomic orbitals, put them together, and you get a good representation of what the molecule actually looks like. Okay, let's see the limitations of this model. We've got, again, carbon. It's got two spots open. Hydrogen. So that might make us think, well, I'm sure the old CH2 compound is coming up. If you think about carbon and hydrogen, you know that's probably not true. Maybe you know what actually would form between C and H would be CH4, this methane. So something different is happening here, okay? There's a problem. If we follow that sulfur example, it'd be CH2, it'd be 90 degrees, and it would look like this L-shaped molecule. That's definitely not the case, okay? So what's happening? We know this is the case. This is what's observed. This is 109.5, this is tetrahedral. This is the reality. So what's happening? The theory is not thrown out. The theory is refined, and it's built to accommodate this. And the way it's done is with hybrid orbitals. So we're going to spend quite a bit of time discussing these hybrid orbitals. It just means it's a combination of orbitals that you already know. S, P, D, and F are combined to form some other orbital, some hybrid of those. So it doesn't look like an S, it doesn't look like a P, it looks like a mix of S and P together. So these correspond with the actual distribution of electrons and chemical bonds. And this really encourage you, those that are committed to going on in chemistry past this, this is a very common topic in organic chemistry. What is the hybrid orbital of these molecules? What do these look like? So One thing I want to highlight is the terminology localized. We're talking about orbitals, and these orbitals are on specific individual atoms. Okay, they have different shapes and energies, but they're on individual atoms, and then the bonds are what happens when we overlap these. So hybrid orbital, standard orbital, you can see it looks different. So the standard, we have this nice symmetric orbital. This hybrid orbital, look at the large amount of electron density region out for bonding. It wants more overlap, so this is, say, the central atom, this is out for bonding, and then we could have one on this side and one on this side. So this is really maximizing bonding. This is a hybridized orbital. So there's some rules that we need to be aware of for hybridized orbitals. The first, the total number of hybrid orbitals equals the number of atomic orbitals you start with. Okay, this will always be the case. The shapes and energies of hybrid orbitals are determined by the combination. What atomic orbitals are combined, that tells us the shape. Again, these shapes are going to be very familiar to you. This is previous VSEPR shapes, so nothing new here. We're just now describing these shapes. How do you get to these shapes in a different way? And just like we saw with hydrogen on the very first slide, we want to see that this hybridization is going to occur the lowest overall energy of the molecule. So this is looking for stability. So this is looking for that valley or that minimum where it's the most stable. Okay, so we'll start with sp3. What I want you to know is right away you can rewrite this as S and all the P's. There's 3, sp3. And if you take a look, that's 4 electron regions. Okay, so I want you to equate the number of letters with the number of electron regions. So for carbon, we already saw it had the 2 s electrons, and then it has 2 available. However, we know it bonds with hydrogen 4 equivalent bonds, so it has to be hybrid orbitals. It's not atomic orbitals that form these bonds with hydrogen. So you can see here, these are 4 equal hybridized orbitals. A couple things I want to point out here. One, it's lower in energy or higher in energy, so it's in between the 2 orbitals in energy. And they're equivalent, so now we have a valence electron in each spot available for bonding. Okay, so again, the sp3 comes from 1s orbital and 3p orbitals. And guess what? It's that special tetrahedral shape that you know, 109.5. So now you think 4 electron regions, 109.5, you now add the piece, that is sp3. So you can see the combinations. This is the S, these are the 3 P's, and these are showing the 4 sp3s in the tetrahedral arrangement that you've known from last chapter. So this is sp3 tetrahedral. So then, of course, if you have sp3 carbon and you've got the s atomic orbitals of hydrogen, they can overlap and form bonds. Those are bonds in each of those locations. So I really want to emphasize again, sp3 is the electron regions. So here you can see Lewis structure. We had ammonia, and we said, what's the electron geometry? That's also tetrahedral because of those lone pairs, but it has 3 bonds. Okay, and then we would say, what's the molecular geometry? That was last chapter. This chapter I want to point out, that's an electron region, and all of these are for a total of 4, so that still gives us that this nitrogen is hybridized to sp3. So sp3 could be 4 single bonds like carbon, or it could have a lone pair or 2 lone pairs, and so on. Next hybridization I want to look at is sp2. So again, it's going to involve one s orbital, two p orbitals, and please note there is one leftover p. Okay, we'll come back to this p. It's going to be very important. But what we have is sp2. So remember, if it's sp2, we can write it out. That's 3 electron regions. That's trigonal planar. We saw that last chapter. So that's still the same case, 3 electron regions. We've got here trigonal planar. Don't forget this one, okay? So trigonal planar, sp2 now, same as before, 120 degrees. Again, the shapes aren't the new piece of this chapter. It's knowing the orbitals and the name of the orbitals, sp2, and a bond is defined as overlapping these orbitals. All right, so let's look at formaldehyde, CH2O, and you can see hydrogen's available for bonding. Oxygen's got 2 places here, and we've already seen carbon can hybridize because it's not going to just have 2 bonds. Okay, so this next slide can be a little overwhelming, but we'll go in a little bit of detail here to try and figure out what's going on. Pay special attention in this case. The carbon is going to hybridize to sp2, so that means there's 3 bonds that are going to happen, and that's that 120 degrees, and then there's going to be this leftover p that we'll talk about in the next slide. So if you look here, there's a lot going on. I want to point out a few things. First, remember we talked about sp2. That was this 120 degrees. That's right here, the purple. Okay, so that's trigonal planar right there, sp2. So that's our sp2 hybridized orbitals. We already said hydrogen is made up of s, so the s from hydrogen overlaps with the sp2 of carbon and forms these bonds. Oxygen is not a central atom here. Okay, so please note hybridization. In our cases, we're going to simplify this. This only happens with central atoms. So anytime you see a terminal atom, outside atom, you think atomic orbitals. So that's why we looked at hydrogen. That's S. Oxygen's terminal. That's a P. Okay. So here, this bond is an overlap of sp2 carbon and a P from oxygen. Remember, we had a leftover P from carbon. P orbitals, remember the bilobe shape? You can see over here, vertical, up and down, and oxygen also has a P orbital, vertical, up and down. So now what we're seeing is actually a bond up and above and below in between the atoms. Okay, so this is a new type of bond. This is sigma bond and a double bond. This is pointing out the difference. Okay, so remember when we did this in Lewis structures, they all look the same. Okay, but what we're doing here is really specifying the difference. Okay, so we have this orbital from carbon, this orbital from oxygen. That's the sigma bond when it's between the atoms. Okay, then we have the leftover p orbitals. That's side to side. This is end to end. So pi bond is here, and that's one pi bond. I know it's above and below, but just remember p orbitals are 2 lobes, so it's only one p orbital here, so that's only one bond between these 2 p orbitals. So now you can see this double bond actually is very different than just 2 single lines like that. It's a sigma bond between the atoms, and it's a pi bond above and below. So the pi bond is just out of the p orbitals, and the sigma bond is from the hybridized sp2 and the p oxygen. So we'll go into great detail about how to distinguish what the bonds are, labeling, what orbitals are involved. But this is, I know, very overwhelming, a lot going on at once to see, but this is highlighting there are pi bonds, there are sigma bonds, there's atomic orbitals, oxygen and hydrogen, that overlap with hybridized orbitals. So we'll do a few more examples like that. So I emphasized this on the last slide, but just wanted to point out again, a pi bond is above and below the atoms, and that's side-to-side bonding. That's a pi bond. The sigma bond is in between the atoms. So your atom is here, atom is here. Now this is a bond in between called end-to-end. That's the sigma bond. So a double bond has one sigma, one pi, and a triple bond, we'll see that a little bit later, actually has one sigma and 2 pi. Okay, so here's what's going to be asked of you. Okay, this was exam 2, draw the Lewis structure, and you're going to be given instructions on draw the orbital hybridization and bonding scheme. Okay, so the bonding scheme is this. Bonding, what kind of bond is it? It's a sigma bond. Okay, what makes up the sigma bond? It's the sp2 from carbon, those are the purple orbitals, and it's the s orbital from hydrogen. Remember, that's the only orbital hydrogen has, so that's one you can always count on. Hydrogen is bonding with s. Then we have another sigma bond, okay, in between the carbon and oxygen, end to end, so that's still the hybridized sp2 carbon, and remember, oxygen's a terminal atom, so it's the p orbital. Then we have the pi bond, p orbital from carbon, p orbital from oxygen. Pi bonds are always p orbitals. That's what we'll look at, is just pi bonds with p orbitals. So we're going to talk a little bit about this. Definitely see me during office hours. I have the models to show this. Is a lot easier to see with a model. But what we're pointing out here is the difference between a single bond, CC, and a double bond, C double bond C. So if you were to see the model that I could show you, this carbon is bonded to this carbon, and it freely rotates. So if I made the molecule and I showed that the chlorines were pointing at you and said, here's a molecule, chlorines are pointing at you, then I could just rotate around this, and the chlorine here could point away, could point down, and so on. So it doesn't tell you anything about the molecule when you draw these, because this is a dynamic molecule. It moves around, it's free rotating. So that's the key here, free rotation. Big difference is when we have this double bond locked into place. Okay, so you see we've got a bond here, but then we also have the pi bond that's above and below, so that's locked into place, and this chlorine over here and over here can't rotate. So it is fixed in place, so the chlorines are either on the same side or on the opposite side. This is called cis and trans. These are organic molecules. This is really unique chemistry, but the cis and trans properties are very, very different. Okay, so this is a great slide to look at to review bonding scheme. I'm highlighting here. That tells you, is it a hybridized orbital, atomic orbital? Is it a sigma bond? Is it a pi bond? That's great things to review. But really what the focus is on is this double bond restricts rotation. When it restricts rotation, you have to name them differently. So chlorines are on the same side. That's called cis 1,2-dichloroethene. If the chlorines are on opposite sides, then that's trans 1,2-dichloroethene. The compound before, remember, this can rotate around, so you don't have to say cis or trans, because this chlorine can be all over the place. This chlorine can be all over the place, so that doesn't need a special name. These are locked into place because of these double bonds, so you need to distinguish which one you have. So let's continue with the hybridization. As I already alluded to this, if you have an S and P hybridized orbital, you got 2 leftover P's. So what's going to happen with p orbitals? What kind of bonds are they going to be involved in? Okay, so we'll come back to that. But if we have sp hybridized orbital, you can think of 2 electron regions, and that should take you to that 180 degrees linear arrangement. If you got 2 electron regions around a central atom, that's going to be linear. So that looks the same as well as the geometry you saw in exam 2. So the real key is now being able to identify if it's linear. That tells us this is sp hybridization here. So those leftover p orbitals, we talked about that. That's right. Pi bond right here, and we actually have another pi bond. See here and here. So 2 pi bonds from those 2 leftover p orbitals. Sigma bond between carbon and hydrogen, and don't forget triple bond. It's going to be made up of 1 sigma and 2 pi bonds. So we added geometries in CHEM200, and that's what we're doing with the hybridization as well. So remember, trigonal bipyramidal, that's 5 electron regions, and that's 5 letters here. So that's trigonal bipyramidal, that's the axial equatorial, that's our difference of 120 degrees, and we also had 90 degrees, these angle differences here. So nothing new, shapes. The new piece is we're calling these hybridized orbitals, and when the orbitals overlap, now we can do bonding schemes. So that's our trigonal bipyramidal, s orbital, p orbitals, and that's the D. So remember when we said we could expand the octet, that's period 3. That's because period 3, energy level 3 has the D electrons or D orbitals for that. So if we add here, look, this is a trigonal bipyramidal. We can recognize 5 electron regions, and those are sigma bonds. So the central atom is hybridized, the terminal atom is not hybridized. And if you look at fluorine, it has a 2s2 that's filled, and then it has a 2p5. So it has 1 spot for bonding here. That's why we're using the p orbital, not the s orbital for fluorine. So all halogens will bond with that p orbital. And our last one, sp3d2, so you can see that's 6 electron regions. That's our octahedral, 90-degree angles that we've seen, and we're adding more d orbitals to this. So again, this hybridized orbital, you can see the energy change, changing this s and p and the d's into an energy level that's in between those, and now those are all available for bonding. This is sulfur hexafluoride, so hybridization, sp3d2, and mentioned again the fluorine with a p orbital. So the good news to review, if we look here, these should be shapes that you recognize. Okay, once you feel confident in these shapes, that's exam 2. Got all those shapes here. So that's electron regions. The piece that we've added then, sp, is 2 letters, 2 electron regions, 3 letters, and so on. That's a nice little pattern that you can rely on to get this hybridization down as you get started here. So that's the key. That's the new piece, the hybridization scheme. All right, so I'll give you a quick check. So go ahead and pause if you want to work on this one. So this is a good review. Remember, we're going to have examples where we have multiple central atoms. So boron's a central atom, and it was also an example of the incomplete octet. So there's only 3 things coming off of boron. Hydrogen's a terminal atom, so those are coming all the way off the very end. and then oxygens in between all those borons, okay? So the question is predict the hybridization, okay? Remember, right off, if it's a terminal, hydrogen, 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 they cannot hybridize, okay? There's no hybridization there. It would only be the s orbital that would overlap to form bonds, no hybridization. So then if we get, the next one we look at is the oxygen. We count the electron regions. There's 2 lone pairs, and there's 2 bonds on every one of them, okay? So that's 4 electron regions. That's 4 letters. That's sp3 hybridization, okay? Boron has only 3 electron regions around it. That's this sp2 hybridization. So that's this 120 degrees trigonal planar. This would be our tetrahedral 109.5, but again, because we have lone pairs, we'd say that's less than 109.5. All right, so where we're finishing then, this is what's expected. This would definitely count on questions coming like this. Write a hybridization and bonding scheme for acetaldehyde. So you don't have to know what acetaldehyde is. I'm giving you the structure here. But you definitely need to know hybridization and bonding scheme. So go ahead and pause it, take a look, and start working on this one. What I really want to emphasize here is it does not have to be like the pictures in the book, okay? So the pictures in the book, I'll give some homework examples. You can look in the back of the book. They're amazing pictures. It looks really great. It can be really simple for this hybridization and bonding scheme, okay? So I'm going to try and draw here and not overlap with the picture when it comes up. But what I'm starting with is this end here, okay? So that's going to be a tetrahedral arrangement. And we're going to see that 3 of those are overlapping with hydrogen. Okay, so I'm drawing in the CH3 group, and I'm going to point out that that's a sigma bond, and that sigma bond between the carbon, sp3, and remember the hydrogen's always going to be S. So that's the bonding scheme and the hybridization, sp3, of this part of the molecule, okay? So then that gets us to the next part of the molecule, and you can see there's 3 electron regions around this carbon, okay? And there's a double bond, so the double bond should be a red flag. That's a leftover p orbital here, okay? So I hope you're seeing the emphasis here. It does not have to be pretty, okay? So now this is the oxygen. Okay, so this is an oxygen carbon overlap there. And now I'm drawing the pi bond from the p overlap, okay? So what we have then is I just drew the pi, and that's from the carbon P to the oxygen P. Don't forget, we also have a sigma bond between the carbon and oxygen, and that's from the carbon, which is sp2. So remember, there's 3 electron regions, 3 letters, and oxygen is a terminal atom, so it's just using its p orbital. Okay, so we have the hybridization, sp2 for the sigma bond. It's not hybridized for the pi bond, and it's the p orbitals for the oxygens. Okay, so we've got our sigma bond, our pi bond, our sigma bond here. We're left over with this one right here. And remember, we can draw in the s orbital for hydrogen. So that's another sigma bond. This one's a little bit different though, because this is coming from the sp2 carbon to the s hydrogen. So for sure, this is not pretty. This is not super impressive, but it's the same, in my mind, representation of the answer here, okay? You've got these beautiful, colorful drawings here with the electrons drawn in. All of this looks really nice, but look, bonding scheme, sp3 to s, we got that. P to P, pi, we got that. sp2 to P, we got that. And then sp2 to s is here. What are we missing? We're missing this one. Okay, forgot that one right there. That's the sp3 carbon connected to the sp2 carbon. So really encourage you to look at the homework. This is part 1 of chapter 6, valence bond theory. We'll add a new theory next part.